You know when a video game crashes, but somehow your whole computer doesn't go down with it? Have you ever wondered what stops that from happening? Well, it's not magic. It's actually one of the most brilliant and fundamental ideas in modern computing. And today, we're pulling back the curtain on that invisible wall between kernel and user space.
Right, so let's set the scene. We've all been there. You're deep into your work, maybe you're in the middle of a game, and then bam, the application just freezes up. It's totally unresponsive. You get that spinning wheel of death. Now, it's super frustrating for sure, but take a second and think about what doesn't happen.
Your music, it probably keeps playing in the background, right? You can still switch over to your web browser. Your operating system is chugging along just fine. How is that possible? I mean, why can one program completely fall apart without causing a total system meltdown? That is the core question we're going to answer.
The secret lies in this really elegant design choice. See, instead of just letting every single program run wild with total control over your machine, the operating system creates this powerful separation. It acts like a very, very strict supervisor for everything that's running. It basically splits the entire environment into two completely different zones. Think of them as two separate realms, each with its own set of rules and its own level of privilege. On one side, you have all your apps, and on the other, you have the all-powerful core of the entire system. So these two worlds are called user space and kernel space. User space, that's where all your applications live. Your browser, your games, your word processors, all of them. They run in what's called an unprivileged mode, which means they have very limited access. And then there's kernel space. This is the VIP section, the inner sanctum. It's where the operating system's core, the kernel, runs in a privileged mode with complete and total access to all of your computer's hardware. A good way to think about it is like this. Kernel space is the protected fortress. It holds the keys to the entire kingdom. We're talking all the hardware. User space, on the other hand, is like the bustling city outside the fortress walls. The applications can do their thing out there, but they are always under the watchful eye of the kernel inside that castle.
Okay, so you might be wondering, why go to all this trouble? Why create this complicated separation? Well, it's not just for fun, I promise. This architecture serves a few absolutely critical purposes that frankly make modern computing possible at all. This separation gives us three massive benefits. First up, protection. A buggy app can crash all at once, but it can't crash the kernel. That wall holds strong. Second, security. A malicious program can't just directly access your webcam or start reading your files. No way. It has to ask the kernel for permission first. And finally, stability. The kernel runs in its own isolated world, which ensures the core of your system stays rock solid, no matter what crazy stuff your apps are doing.
All right, but this brings up a pretty obvious new question, right? If these two worlds are so separate and all the apps are locked away in their little unprivileged space, how do they get anything useful done?
I mean, think about it. To save a file, an application needs to talk to the hard drive. To show something on the screen, it needs to talk to the graphics card. But we just said they can't access any hardware directly. So, what's the deal? How does that work?
Well, they have to ask nicely. An application running in user space has to go up and formally knock on the kernel's door and request a service. It can't just barge in. It has to go through a very specific, very controlled process.
Let's walk through a real example. Let's say a program wants to print the word hello. Step 1, in user space, it calls the printf function. Simple enough. Step 2, but printf can't touch the screen directly, so it makes a system call to the kernel asking for help. This is the knock on the door. Step 3, the very instant that system call is made, the CPU switches from user mode into privileged kernel mode. Step 4, now that it's in control, the kernel accesses the screen hardware and prints the text. And step 5, and this part is absolutely critical, the CPU immediately switches back to unprivileged user mode and hands control back to the application. And that knock on the door has an official name. It's called a system call. It is the only legitimate bridge between these two worlds. It is the secure, official way for an application to ask the kernel to perform a privileged task for it. So now we get the architecture, we get the rules. Let's look at the high-stakes consequences of this whole design. What actually happens when something goes wrong inside each of these two spaces? And here, right here, is the real payoff of this design. If an application in user space has a fault, if it crashes, the operating system just terminates that one program. Your browser dies, but your computer is totally fine. But If a fault happens inside kernel space, say from a buggy device driver or something, there is no safety net. The kernel itself crashes and it brings the entire system down with it. That's a kernel panic. That's your blue screen of death.
So when you get right down to it, this simple but incredibly powerful idea of separating the system into two distinct worlds is the absolute bedrock of the stability we all take for granted. It contains the damage from faulty apps and protects the core of the system at all costs. This design is in your phone, it's in your laptop, your servers, it is everywhere.
So the next time you have to force quit a frozen application and your computer just keeps humming along without missing a beat, you'll know exactly why. It isn't luck. It's that powerful, invisible wall between user space and kernel space, doing its job perfectly.